Hello everyone and welcome back. Today I'm gonna talk about entropy and the idea that I'm developing to extend it. Entropy began in classical thermodynamics with the ideas of class use in order to connect the heat given to the system or taken out to to the system's temperature. But then, with the ideas of Boltzmann, he was able to introduce some statistical axioms about that system and the particles in it to its entropy. And that genius idea was able to connect two different unseemly fields in physics to each other, namely statistical mechanics to thermodynamics. Of course, by the time Boltzmann was developing statistical mechanics, there wasn't such a field. So statistical mechanics actually begin with these ideas. So they are so fundamental to today's physics. But the thing is, in the beginning of the 20th century, a new field rose up called information physics. Information theory. It actually isn't a part of physics, but I'm talking about physical concepts because in today's game, let's say in physics, information theory is at the center of quantum mechanics, so it's kind of like information physics that I'm referring to, because I believe that in the future, the next step that physics will take will put the concepts of information theory to the fundamentals of physics. It will be unlike, for example, in the quantum mechanics. So I'm not talking about entanglement and the way to quantify those kind of characteristics. I'm talking about being and utilizing the properties of information theory at the center of physics itself. So let's get back to our story. So what I'm trying to say is that with the ideas of Boltzmann, we were able to connect and give a new definition of entropy, and with that new definition, we are able to connect two unseemingly different fields in physics. And then, of course, thermodynamics evolved and it became part of statistical mechanics, and it's actually like the asymptote of statistical ideas, it has been shown. But the thing is, with the rise of information theory, a new definition for entropy arose. It's not actually a new definition, it's just the application of the concept of entropy to a communication channel. And this idea was given by Shannon, and that's why we call it Shannon entropy. Shannon, an electrical engineer and mathematician, he graduated from Michigan, then moved on to MIT, and then go to Bell Labs. And while in Bell Labs in 1948, I actually have the book, The Mathematical Theory of Communication, he was able to give that definition. And while he was visiting Institute of Advanced Study at Princeton, which is still a legendary place for physicists and mathematicians alike, there was a figure in that place, Johnny von Neumann. He was a great physicist, a great mathematician, as well as a great computer scientist, and he was actually the father of the communication age. We all know, von Neumann's architecture in computer, let's say, architecture. So what I'm trying to say is that while he was at Princeton, he was talking about his ideas to Johnny von Neumann, and von Neumann immediately recognized the concept that Shannon was talking about, the entropy. So that's why, I think one of the reasons why Shannon called it the word entropy is because of his interactions with Johnny von Neumann, and then John von Neumann introduced the same concept to quantum mechanics, and today we know it as John von Neumann's entropy in quantum mechanics, but it is basically the concept of Shannon entropy applied to quantum systems and our ability and our impositions of information in quantum mechanics. We are able to deduce some characteristics about information theory in quantum mechanics. But the thing is, the evolution of the concept of entropy is something distinct. So what I'm trying to say is that the concepts that were first developed by, let's say, class use in classical thermodynamics, then by Boltzmann, and then by Shannon via von Neumann, we are able to implement it in quantum mechanics. So we have three different fundamental definitions for entropy. The thing is, the two of them, Boltzmann's entropy and class use entropy, were shown to be the same. but not exactly the same. The one is the asymptote of the another. You see, there's a subtle difference. Because a classical concept that entropy was first introduced with is just a quantity that connected heat given or taken out of the system to the temperature increase or decrease of the system. But connecting it in a statistical nature by counting the microstates of that object and the degree of freedom of that system to be taken something quantitatively and taken to be an entropic law is an axiom. So what I'm trying to say is that it's so majestic that two of those formalisms are able to connect in such a fundamental way. But the same is not true with von Neumann's entropy and statistical entropy, Boltzmann's entropy. So one is not equal to another. In terms of advanced concepts, actually, under certain circumstances, if you take temperature in a high environment, it can be shown that von Neumann entropy becomes thermodynamic entropy. But this is not always the case. If you think of a star has two different entropy in itself. Because every system in the universe is a quantum system, it has to have a von Neumann entropy. But we use von Neumann entropy only to quantify some of the properties of the information content of the quantum system. And every evolution in quantum mechanics is unitary, meaning that von Neumann entropy of a given system doesn't change with time. But thermodynamic entropy necessarily has to increase with time. This is the second law of thermodynamics. So how can one obtain one definition from the other? The answer is we can't. So why are we calling it the same name? Well, you see, the physicists are like architects. So it's not mathematics. Physics is not mathematics. So when we use a word, let's say, for example, a metric, it has a absolute meaning in terms of mathematical concepts. But when physicists are coming up with new, let's say, theories, what they do is that they look at similarities, they look at analogies. So when von Neumann saw the definition of entropy in Shannon's work, he assumed that it has to be something similar. It has to look, their fundamentals need to be the same. That was von Neumann's vision. But this isn't always the case, similar to in this discussion. So what I'm trying to say is that there's something missing, a connection, a new definition needs to be formulated in order for us to talk about a concept that is universal. So when we are talking about a concept like entropy, it is something that is changing. But how can a singular definition have different meaning in physics? This is a philosophical argument as well. It actually began with Hilbert. In Hilbert's 20 problems that he came up with in Paris in 1900, Hilbert's programs, let's say, was to reformulate whole of physics in terms of axiomatic approach of mathematics. But of course, we failed. We don't have the whole physics in an axiomatic format, and the way the physics is done is that there are some flag bearers, there are discoverers like Einstein who come up with new theories, with ideas that are not formal. So you are bold, you are introducing new concepts constantly, you are trying, and suddenly it works out. But then the theory is not complete. Some other mathematicians, like let's say, in terms of, let's take the development of special relativity, when Einstein developed his ideas, there were a swarm of mathematicians that attacked the problem and make it and formulated it in an axiomatic way. This is also needs to be the case for thermodynamics as well. So von Neumann, when he called the term entropy, it was an assumption. You need to prove your assumptions. But the thing is, it turns out that they are two different concepts, and calling them entropy is a misconception on our part. But what do we mean by entropy? And if such a thing is so fundamental, then then why we call it in the same name? I mean, why its definition distinguishes itself from different field to other fields, let's say.